Let's wrap this section up, huh? So we're going to plot a polar curve, which means we're going to graph a polar curve. And the first thing we're going to do is what's called a cardioid. Kind of looks like a heart, or if you're a child like I am, it might look like a butt. You know? Depends on who you are. So let us go through and graph r equals 1 plus cosine of theta. But we're going to plot this in polar, right? Where, remember that if you had a point that was like 1 comma pi over 4, be like, all right, pi over 4 is right here. Let's go 1 unit. And yeah, then we'll start to graph it up. Okay. But thetas are independent variable. That's what's going to determine. So that's like our x. Even though, you notice how it's kind of written back. Wouldn't it be nicer if it was theta comma r? I don't know why they did it that way. That's kind of strange because that's backwards. Our independent variable is the second one. Huh, weird. So let's go through and plot some points, but let's look at something. Patterns, y'all. We don't want to have to do too much work. If you see just a cosine, cosine goes with x, right? So we know that we're going to have symmetry. So if we graph this thing and it looks like this on this side, well, we know it's going to look like that on the other side. That's kind of what it looks like. Oops. There's symmetry. If it was y, it would be symmetric about the y-axis. Or it just could be symmetric about the origin. Patterns. You don't want to do extra work. I remember doing this when I was a Calc 2 student. The teacher's like, I think she gave us 4 of these to do by hand as a homework assignment. Oh my goodness, plotting them took forever because I didn't know trig and I didn't know any polar. I knew a little bit of trig, but I didn't know enough about the symmetry. So hopefully I can help you through it. So let's start with a simple number like 0. Let's plug that in. And I'm going to have to go along with the assumption that you got this. I can't be plugging it in. Cosine of 0 is 1. 1 plus 1 is 2. Thus, we have a point, 2 comma 0, where the angle is 0 and the radius is 2. So let's just call that 2 and put a point right there. Now, let's not do every single one of them. Let's skip some stuff. Let's not do pi over 6, pi over 4, pi over 3, pi over 2, 2 pi over 3, 3 pi over 4, 5. No. Let's keep it a little bit more mellow. Let's go with pi over 4. Let's just cut this thing in half, right? Let's cut it in half and let's see what we end up with. So this one, I'll write it out. So we're saying r is equal to 1 plus cosine of pi over 4. Well, that's 1 plus root 2 over 2. What the hell is that? Dude, that's a... I don't know, man. I know it's bigger than 1, but I know it's smaller than 2. Root 2 over 2, it's about 0.7. What a crappy number. 1 plus root 2 over 2. Okay. Comma pi over 4. Well, let's go to the pi over 4. I'm just going to kind of draw a line and go, well, it's not quite as long. It's not quite as long. It's 1 plus root 2 over 2. It's not quite 2. The radius is a little bit shorter, but we're at pi over 4. So this length there is 1 plus root 2 over 2. You can use a calculator through this part. You'll have a calculator on your final. So if you want this, I don't know whether we'll be doing too much graphing. If you know what things look like and you know the symmetry, you might be able to skip over this. Okay, let's go to pi over 2. And let's plug that in. Now this one I can do pretty quickly. Cosine of pi over 2 is equal to 0. So 1 plus 0 is equal to 1. So we have 1 comma pi over 2. Sweet. Sweet. I think I made this one a little too far away. Let's make that a little closer. There we go. And then we'll call this one 1. Right there on the y-axis. So that point there, which we have at 1 comma pi over 2. Now let's jump to another one, and I'm just going to choose a random one. And this is totally not random. I know that cosine of any pi over 3 is a half or negative 1/2. So let's go this way. Let's choose 2 pi over 3. It would have been smarter to choose this as pi over 3, because then we would have ended up with 3 halves. So it might be smart if you're doing sine, you want to use your pi's over 6s, right? Because those are halves. You're seeing that if we don't know trigonometry, we are hosed. We got to know it. So 2 pi over 3, well, we plug that in. I'll do this one. Pi over, oops. 2 pi over 3, let's pop it up over on the side. That is not what it equals. But cosine of 2 pi over 3, we're in the second quadrant where x's are negative, so it's 1 minus a half, which is equal to a half. So we have a point at 1/2, comma 2 pi over 3. So 2 pi over 3, that kind of lives like that direction. So let's call it about a half. It's just getting closer. All right, it's not quite as far away because we're only at a half instead of 1. Maybe bring that down even a little bit closer to right here. And then let's plug in pi. And then we're done if we recognize symmetries. Well, if you plug in cosine of pi, that's my favorite. That's -1. So 1 plus -1 is 0. So we end up with 0, comma pi. Oh, so it comes into here. Let's just draw a nice smooth surface. And we have symmetry about the x-axis. If you were to plug in 4 pi over 3, you're going to still get a half. If you plug in 3 pi over 2, I'm just kind of like working back my way back up from pi, right? We had pi's over 3, pi's over 3. Then we went to pi's over 2, pi's over 2. This is also going to be 1. And man, we have symmetry. So now what we can do is just kind of draw it out. I mean, like, there it is. It's a little heart. It's a cardioid. And in section 12.3, we're going to go find the area of said cardioid. Okay, there's one of the choices. Let me write those in. 1/2, comma 4 pi over 3. And 1, comma 3 pi over 2. There would be some points, and we just plot them. Again, use Desmos if you need a little bit of help seeing them at first, because they're somewhat tough to graph, but we're going to keep it simple. We're going to do cardioids, or what's called a rose curve. But the cardioids can sometimes be graphed a little bit differently. I'm going to show you in just a second, but we're going to also do what's called a rose curve. And a rose curve, or a 4-leaf rose, let's say R maybe is equal to sine of 2 theta. So if you ever see like a double angle looking thingy, it's a rose curve. And that's symmetric about the origin. It kind of looks like this. Got little petals on it. Of course, I can't draw, but it would all be symmetric, and that's what those look like. If this was a 4 in there, there'd be 8 petals. If there was, well, whatever. So let's go to Desmos and just take a look at a few of these. All right, Desmos. Let me click this little bullseye-looking thing, and yeah, there we go. That should be super helpful. So let's deal with other cardioids. Didn't we just do this one? R is equal to 1 plus cosine of, and if you need your theta, it's in the ABCs all the way over to the right. Hey, look! Didn't we just graph that dang thing? I'm pretty sure we did. Well, what would happen if this first number wasn't a 1? What if it was a 2? What would it look like? Okay. All right. Well, what if this was a sine? So cosine goes with x, right? Isn't that symmetric about x? If I change it to sine, look at that. It's symmetric about y. Sine goes with y. Cosine goes with x. So whenever we're doing these cardioids, we're going to have symmetry about whatever we have there. It makes it a lot easier. You're only going to plot a little bit of it. And you don't necessarily have to know exactly how it's graphed, but you got to have a basic idea, because we're going to have to cut these things in half when we integrate them. And we're going to need to know which numbers to go through. Now let's play a game. So if I add a number in front of sine, right here, that's positive, we're going to create what's called an inner loop. Now that looks like something. Now, I'll stop being a child. Yeah, it creates a loop. That's because of negative radii that pop back the other direction. That's how we end up creating inner loops. Now, if we change it to cosine, what do you think is going to happen? Huh? Now it's symmetric about x. Now, what do you think is going to happen if I change this to a 1 minus 2 cosine? It flips the other direction. Huh. So there's some pictures. All right. Now let's move into some rose curves. So sine of 2 theta. Yeah, look at that. Nice little thing. Now watch. Let me go to 4 theta. So how many petals are there right now? 4, right? Now there's 8. Now there's 12. Now there's 16. Now there's 20. Now there's 200. And I can never help myself. All right. Enough of that. So that's what we call a rose curve. Notice it's symmetric, not just about the x-axis, but the y-axis. So if you were to encounter a rose curve, if I was to ask you to integrate something like this, to find the area, shoot, you'd only have to do one of those petals and then multiply by 4. That's kind of convenient. But what happens if we have a 3 theta? Didn't you notice I did all even numbers? What the heck is happening? Why is there only 3? When there's 4 theta, we get 8 petals. We double it. But when we do 5, there's only 5. It's because it repeats upon itself. But do we still see that there is a sine? Don't worry about that last part. Sine. Yeah? Sine? Sine goes with y. This is symmetric about the y-axis. If we made this cosine of 5 theta, it's now symmetric about the x-axis. So we'd only have to do a little bit of it. All right, that's plenty. That's good. We're going to get into some graphing. We're going to do that in section 12.3 when we start finding the area inside of these. And others. Oh, the fun we will have. But it will be the last session of Calculus 2. And everybody can get stoked about that. All right, I'll see you in 12.3.